In black water, a gulper eel opens a mouth that suddenly seems larger than the animal carrying it. The image suggests a predator built to swallow giants. Yet that familiar explanation misses the mouth's likely advantage. Eurypharynx pelecanoides is slender, soft-bodied, and dominated by jaws that expand into a broad, delicate pouch. Its common name invites comparison with pelicans, although water and prey move through a very different feeding system. The central mystery is why such an enormous opening belongs to an animal with such a narrow throat. A wide gape can surround prey, but the passage behind it constrains what can actually reach the stomach. Direct observations show gulper eels expanding their mouths, while stomach studies usually reveal relatively small food. That mismatch shifts the investigation from swallowing massive victims toward intercepting scarce, evasive targets. The mouth may work as a net-like volume, increasing the chance that a nearby animal cannot slip aside. It may also display or threaten, but those roles remain less securely documented than feeding anatomy. If you saw only the expanded silhouette, scale would encourage the wrong story. The gulper eel's real achievement is not defeating a whale-sized meal, but making one brief encounter harder to miss. Its jaws transform a thin hunter into a temporary capture surface within an almost empty landscape. To understand that transformation, anatomy must be separated from dramatic reconstructions that exceed the evidence. The investigation follows the mouth from folded profile to expanded trap, then tests what can pass beyond it. Gulper eels inhabit deep pelagic waters across much of the world's tropical and temperate oceans. Adults occur far below sunlit surface layers, where ambient light is extremely weak or absent. Their bodies are long and laterally compressed, ending in a tapering tail with a luminous organ. The head appears small when the mouth is closed, because the jaws and membranes fold alongside the body. When opened, elongated jawbones spread, and the flexible floor of the mouth bows outward. This creates an impressive cavity without requiring a permanently heavy skull or thick chewing muscles. The teeth are small, consistent with retaining modest prey rather than cutting powerful animals into sections. Behind the spacious mouth, the esophagus remains comparatively narrow and limits the diameter of swallowed material. That verified constraint is the first decisive clue against a simple giant prey interpretation. Stomach contents have included crustaceans, fishes, and cephalopods, generally small enough to pass through the throat. Digestion often makes identification difficult, so cautious accounts avoid assigning species from featureless fragments. The gulper eel does possess an expandable stomach, but expansion alone does not erase every anatomical bottleneck. Popular imagery sometimes treats open jaws as proof that anything enclosed can be swallowed. Enclosure is only the capture stage. Prey must then be retained, oriented, transferred, and digested. Its musculature is suited to slow, deep water movement rather than sustained, high-speed pursuit. Energy conservation matters where meals arrive unpredictably, and each chase can consume a meaningful fraction of reserves. A large opening can compensate for limited acceleration by increasing the space swept during a short lunge. If you imagine catching drifting seeds with a narrow tube, Most pass around the edges, widen that entrance suddenly, and the same movement intercepts a larger parcel of water and its occupants. This analogy clarifies the geometry, though living prey can sense flow and actively escape. The gulper must therefore balance gape size against drag, timing, and the risk of pushing prey away. Its remarkable mouth is best understood as a flexible capture tool, not an unlimited swallowing chamber. One mainstream hypothesis holds that the eel approaches small prey and rapidly expands its oral cavity around them. Water entering with the prey must later escape, likely through the mouth or gill openings as the jaws close. The exact flow pattern has not been completely measured in freely hunting gulper eels. Without those measurements, calling the mechanism suction feeding may overstate how much pressure difference actually develops. A broad scoop remains plausible, even if suction contributes little to initial capture. Video of living individuals has recorded mouth expansion and body postures, but encounters are brief and context matters. Some filmed expansions occur near submersibles, whose lights, motion, or electrical presence could alter behavior. Such footage directly documents capability, not necessarily the purpose of every expansion in undisturbed darkness. Researchers compare these sequences with jaw structure and stomach contents to identify the explanation, requiring fewest assumptions. Small prey plus a narrow throat support, interception, more strongly than routine consumption of enormous animals. The luminous tail tip has inspired a separate hypothesis that it might lure prey toward the mouth. Bioluminescence is real, but a complete natural sequence of luring followed by capture is not established. The tip might serve communication, defense, distraction, or another function that remains unknown. Its distance from the mouth also makes simple anglerfish style luring an uncertain comparison. You should therefore picture several testable possibilities, not a single cinematic behavior presented as settled fact. Another proposal treats extreme mouth opening as a threat display against approaching animals. An expanded dark cavity could make the eel look larger, yet reactions of natural predators remain inadequately observed. Still, multiple possible functions do not carry equal evidence, and feeding geometry remains tied most directly to diet. The eel's closing sequence is equally important because trapped animals must be concentrated near the narrow entrance behind. Flexible jaw membranes may help funnel prey, but delicate tissue cannot restrain every strong or spiny target. Selecting small, soft-bodied prey would reduce injury and ease transfer into the esophagus. This predicts stomach contents dominated by manageable animals, broadly matching available records without defining every meal. It also predicts failed captures when prey reacts before the opening fully surrounds it. Failures almost never appear in preserved stomachs, creating a serious gap in apparent hunting success. Until repeated natural footage exists, attack frequency and efficiency remain unknown. The mouth's ecology becomes clearer when placed within the deep scattering community of fishes, crustaceans, and cephalopods. Many potential prey migrate vertically, changing their depth across night and day while following food and avoiding predators. Gulper eels occupy this moving environment, without reefs, vegetation, or solid surfaces that could corner a target. Their capture field must be created from the body itself, appearing for seconds and folding away afterward. When you follow the jaws through that sequence, their size becomes an answer to open space. The eel approaches slowly, a prey item enters range, the mouth expands, and escape routes suddenly narrow. If capture succeeds, closure gathers the small animal toward the throat and converts opportunity into stored energy. If timing fails, the mouth collapses, and the eel has spent effort without a meal. That cue-action-consequence pattern favors accurate close-range detection, although the responsible senses remain incompletely studied. Vision may detect bioluminescence, while the lateral line may register nearby movement through water. Strategy also carries costs, because wide opening increases drag and exposes fragile membranes to damage. A cumbersome permanent basket would impede swimming, so foldability is central to the adaptation. The animal gains a large temporary aperture while retaining a streamlined body between encounters. That design illustrates a recurring deep-sea compromise between opportunistic feeding and low everyday energy expenditure. Gulper eels transfer energy from small midwater animals into larger predators when they themselves are eaten. Their lives, therefore, connect scattered prey pulses with the broader carbon economy of deep pelagic ecosystems. Human knowledge comes mainly from trawls, museum specimens, and remotely operated vehicle encounters. Nets can damage gelatinous tissues, while a scent changes pressure and leaves natural posture difficult to reconstruct. Submersible observations preserve posture better, but lights reveal only a narrow and possibly altered moment. Each damaged specimen makes the intact animal harder to imagine, emphasizing the value of careful deep water encounters. The mouth's foldable design links energy economy, prey scarcity, and survival within one lightweight structure. Its small meals support a predator that may later transfer their energy to larger deep-water hunters. That ecological role is quieter than the expanded silhouette, but it gives the structure meaningful biological context. Future low-light recordings could reveal jaw motion, water flow, prey capture, and transfer without imposing a dramatic reconstruction. DNA analysis of stomach material could refine prey categories without inventing identities from damaged remains. Repeated observations would test whether tail luminescence precedes capture, follows disturbance, or serves unrelated contexts. They would also separate normal feeding expansion from defensive responses to vehicles. No single method can answer purpose alone. Behavior, mechanics, and diet must converge. If you return to the opening image, the giant mouth still blooms like a parachute in darkness. Its scale remains genuine, but the narrow throat quietly defines what the spectacle can accomplish. The most supported narrative is a broad interception tool, folding around relatively small, elusive prey. Suction may assist, tail light may matter, and defensive display may occur, but each requires stronger direct tests. The gulper eel is not evidence that deep predators routinely consume anything their jaws can surround. It is evidence that scarce encounters can favor an enormous entrance attached to a modest digestive passage. Every expansion trades drag and vulnerability for a few seconds of increased capture area. That trade reveals adaptation through geometry rather than aggression or impossible appetite. The next successful recording must show prey, flow, closure, and transfer before mechanism becomes fully resolved. Until then, the gulper eel's mouth is best understood as a vast net whose exact cast remains partly unseen.